Good morning.
Good morning.
Okay, so we're going to be, again, talking about propagation of uncertainty. I'll set it up at the beginning. The first part of these notes are the ones that were in PCHEM 1. So if you've been through those with PCHEM 1, the first part will be reviewed, but don't worry, it's not the whole, it's not just a total repeat of what's in PCHEM. So why do we want to propagate uncertainty? This is the main thing. A numerical result without an estimation of its uncertainty is useless, right? So we need to know how certain we are of the numbers, and certainly numbers that we get from someone else. If someone just gives you a number, and this is my big complaint about medicine, you go in and you have a test and they give you a number, you know, that, see, I'm trying to remember, let's just take for cholesterol, for instance, you know, say your cholesterol is, let's say 200, okay, well, 200, is it, what's the units on that, you know, is it, you know, micrograms per deciliter or something like that. I mean, there needs to be a unit on that. Then what's the range? Like, where's the limit where I'm in danger? Okay. And then also, how sure are you? So if it's 200 plus or minus 100 and I'm 50 away from the danger mark, I could be over it. But if it's 200 plus or minus 1 and I'm 50 from the danger mark, then I'm okay, at least at this point in time. And so you see how I've been beating units into your head for a year. But also uncertainty. We need to know how certain we are about the number. What's our plus or minus? And that really makes the number useful. So, and then that danger limit, that's what we call the specification limit. So we don't always have to have specification limits, because we may not have a specification, like people that are measuring steps in a day. You know, there's really no specification limit for that. What's too many steps? What's not enough steps? I mean, if you're sick and you're supposed to stay in bed all day, then 10,000 steps is probably not wise. Okay, so some things don't necessarily have specification limits. So we don't beat that as hard as we do the uncertainty. You know, what's the uncertainty of that number, and then also what are the units on that number? And so then these measurements that are directly measured have easily determined uncertainty. Measure it 3 times and take the standard deviation, you know, or look at the historical behavior with a control chart and see how that process varies. And then you can get the uncertainty that way. So if you have a 4-place balance, you know, if you look at that, it goes to, you know, 4 decimal places. And sometimes these have a maximum mass of 300 grams. And so you see that's quite a lot of orders of magnitude in terms of what that balance can do. It's pretty impressive that it has an uncertainty down in that last digit of plus or minus 2, that it can go. If you want to know orders of magnitude, you can just add those up. And so these are powers of 10 or place value, right? And so it's 1, 2, 3, 4, 5, 6. And I mean, it gets into the 7th order of magnitude, but it stops at 3. You know, it doesn't go all the way to 9. But anyway, that's 7 orders of magnitude. So these balances are amazing. You know, we had one at Pantex that was a balance for forklift pallets. So like they would drop a forklift pallet on this thing and it would weigh to thousands of pounds, and yet it would do like 1/10 of a pound. And it was amazing that, you know, you could have a pallet that could measure to 1/10 of a pound up to several thousand pounds. And I would go over there. We were on a tour, and whenever they took people on a tour of this secure facility, they had to have escorts. And so I was an escort a lot of times. And so they're given the same spiel I've heard in this loading area, that, you know, and I'm over here playing with the pallet mass. I'm putting one toe on it, see if it could measure just the pressure of one toe. And sure enough, I could get it to move 1/10 of a pound. They were like, "What are you doing?" Playing with your scale. So, yeah, they knew I was off. And so then when we do multiple measurements, we have lots of opportunities for uncertainties, little bits of high measurement and low measurement. And so they're a little bit more uncertain. So you might have a balance that measures to 2/10 of a milligram. But then when you run that through a titration or something, there's so much other things going on that you don't maintain that uncertainty. In fact, you want your balance or your scale to be almost insignificant compared to your process. You want it to be really precise, and your process is going to be the thing that limits your precision. And so we incorporate these uncertainties, as we talked about last time, in the mean and the standard deviation. So we're going to be talking about those two values constantly throughout this process. And so we're going to take these operations, whenever we do mathematical operations on our measurements, we have to propagate the uncertainty. We have uncertainty associated with each of these items, right? We have an SA, an SB, and an SC. And we get this result. You know, this might be sort of the average Y. We have these different measurements. We come up with an average Y, and then we need to know SY. So that's the thing that we don't know. We've taken measurement A, measurement B, measurement C, and we've added them and subtracted them and so on. And we need to know what the uncertainty is in Y. Now this is using sigma because we're like assuming we have a population. And so this is the uncertainty for A, the uncertainty for B, and the uncertainty for C. And so whenever you're doing addition and subtraction, it's just the variances added together. So it's those sigma squares that you add together, and that gives you the variance of Y. So it's very simple. And if you just want instead of the variance, if you want the standard deviation of Y, then you take the square root of that sum, and you've got the uncertainty. So these are the variances. And notice these down here, this is the variance divided by A, and this is the variance of B divided by B, and variance of C divided by C. Do you recognize what these pieces are? So there's a name for this fraction. Yeah, this is the relative standard deviation. So it's that standard deviation relative to the mean. You see how similar it looks to this equation up above? Instead of the variances squared, it's the RSDs squared. And so for multiplication and division, you're just dealing with relative standard deviations squared. And you sum those together, and that's the relative standard deviation squared of your result. Because look, if I take this Y and move it over to the other side, I have the relative standard deviation of Y. And if I square both sides, I have the square of the relative standard deviation of Y. And that's for products. So each of these things that we're multiplying and dividing have some uncertainty associated with them. And this is how we get the uncertainty in our result. Exponents is a sort of a simplified case of multiplication. And so you have A to the X equals Y. And so this would be the uncertainty in Y. And, you know, if you look at this, it's really just sigma Y over Y is equal to X times sigma A over A. And so it would be just like this. You would have the, you know, all of those RSDs for A, however many times, X times, and then you would square those and add them together and you get this one squared. And so you can just take the square root of all of those and you end up with this number of relative standard deviations of A. So if something is a squared dependence, then the RSD for Y is 2 times the RSD for A. And then we have logs and anti-logs in case you're doing things like pH and you want to know the concentration uncertainty by measuring the pH, or vice versa, the pH uncertainty by measuring the concentration. And so these are some examples for that. Okay. And so this, I've gone ahead and shown these simplified equations here that the just dealing with the variance or the RSDs. And those are easier to remember, I think, if you just write them out that way. So we'll use these equations in a few examples. Okay. All right, so then we have this simple example for propagation of uncertainty. A metallic object is weighing 2.5 grams plus or minus a certain amount is put into a graduated cylinder, and you could see how much water it displaces. So this is one of our example, or one of our labs for the is it non-majors? 1411, okay, 1411 lab. And so again, volume displacement in water is a great way to measure volume of an object that's irregularly shaped. You know, if it was a cube, you could measure the sides and calculate the volume, but you just do water displacement and look at the volumetric change, and you can tell what's the volume of the object. So we can calculate its density. So that's easy. We can 2.5 over 0.13, and we get this long number in our calculator, and we're going to keep all those digits temporarily. And so that's the point too, is propagating the uncertainty tells you where to round. Because remember, the rounding convention is just keep all the certain digits and one uncertain digit. So we will find out what our uncertain digit is when we round, or when we do the propagation of uncertainty. And then the second question is, can we tell if this is gold, which has a density of 19.28 grams per mil, or tungsten, which has a density of 19.25 grams per mil? And so if we're looking at this, we see that the result says 19.25. And so it looks a lot like tungsten. But without a propagating uncertainty, we can't be sure. So we need to look to see what is our uncertainty, because we have uncertainty in the volume measurement, and we have uncertainty in the mass measurement. Okay. So we need to take this multiplication or division type problem and propagate the uncertainty, which means we need the relative standard deviation for each of the pieces. We're going to square those, add them together, take the square root, and then multiply by the 19.25. So whenever we have that equation of y times the square root of everything, that 19.25 is y. That's our result that we got. And then the first one, it doesn't matter which one, because your addition can be done in either direction. So we could start with the mass measurement, since that's first in the problem. And notice how the relative standard deviation is this piece here, the 0.225 over this piece. So in our little equations that we had earlier, this would be A, and this would be sigma A. So if you're looking earlier on the previous slide, how to make these how to put these together, that would be A and sigma A. And so then you have that relative standard deviation in your result. And then we have the B and sigma B. So this is sigma B here, 0.050. And this is B. And so those go into the problem here, sigma B over B, sigma A over A. And notice it's unitless, right? Because the mils cancel the mils and the grams cancel the grams. And so you can propagate uncertainty with things that have different units, because these ratios cancel all of the units. That's kind of nice. And you get the units of the result in the end when you multiply by A. So our uncertainty is going to have multiply by Y. So our uncertainty is going to have the units of the result that we're looking for. So it's cool that the units work out. So we square these, we take the square root, multiply by 19.25, et cetera, and we end up with 7.6 grams. Now, keep 1 or 2 digits of uncertainty. I've seen both in the literature, okay? But 3 is ridiculous. So 1, 2 at the most. Because again, this is the measurement of your uncertainty. I'm saying I'm uncertain in ones. I'm very uncertain in tenths. It's ridiculous to keep hundredths, because if I'm uncertain in ones, then hundredths is totally a mystery to me. Tenths, the tenth just gives you an idea if you're closer to being uncertain like 8 grams, or if you're close to 7 grams uncertainty. This is right in between. This is 7.6 grams of uncertainty. And so I like to keep 2. It just kind of gives me a little bit more of an idea of how certain we are. And so what we're going to do then is, this is going to tell us to round Y to 1/10 gram. So it's going to tell us to round to that first decimal place. And so this is going to be our reported result, 19.3 plus or minus 7.6 grams. So these have to match place value.
We can expect to see these calculations like on the test.
Yes, just like the practice exam. Yeah. Okay, so when I say match place value, that means they go to the 10th place. Okay, and so there's a problem on there that's like 1 is a mismatch. It'd be 19 plus or minus 7.6. Well, the 19 is missing the 10th place. Or 19.3 plus or minus 8. The uncertainty is missing the 10th place. So they have to have the same place value. They have to go to the same place value. So then what does this tell us for our second question about, can we tell if it's tungsten or gold, right? Well, let's look at where does this uncertainty come from? Okay, well, if you look at our relative standard deviations, let's see which one of these is the biggest. So we can just look at these fractions. Since this is a fraction, we can move that decimal place over 2 on top and move it over 2 on bottom, and see that this is 5/13. So that's a fraction of 5/13. And then this one, we can move that decimal place over. I mean, we can move it over here. Let's just move it 1, because we're dealing with uncertainties. We don't really care about all these extra digits. So this is 2 out of 25. Okay. Or roughly 1 in 12.5. Or 12.5 is close to 13. So this is close to 1/13. This is 5/13. So this is telling us our volume is the thing is the bad number, right? It's the largest uncertainty. So if we wanted to improve our process, we would look at the volume. The volume measurement is what's causing our uncertainty to be so big. It's 5/13 uncertain, whereas the mass measurement's only 1/13 uncertain. So that's a great skill. That's like a ninja analysis of uncertainty. And if you thought, oh, that wasn't that bad, then you're a ninja uncertainty analysis person. Just look at these relative standard deviations of all the stuff that went into your measurement and find the biggest one. And that biggest one is the thing that you can focus on to improve your precision. And what I just showed you is essentially right here with little Gaussian curves. And so the mass, you see how narrow that little peak is in the middle here. This has a small uncertainty of 0.09 or RSD of 0.09, and this has a RSD of 0.38. So if you did 1/13 and 5/13, you'd get these decimals. And this gives us the overall uncertainty in our problem of 0.38. You see the overall uncertainty RSD for our Y is 0.39, and the volume itself is 0.38. See how close together they are, how similar they are? This is telling us that the majority of our uncertainty is from the volume measurement. So there's different ways to analyze that. I like to use the fraction method. Just look at those in that problem and see which is the biggest fraction. Okay, so here we are in our measurement, 19.3, and we were trying to tell the difference between tungsten and gold. And so if we took that mean and the standard deviation, so the standard deviation of our result is where you see how this is curving up. And when we get up here, it's curving down. And where it switches, when this curve switches from going up to going down, is the inflection point. So somewhere in here is the inflection point. I'll just point right there. And it's the connection of those two inflection points that defines sigma. Okay, so if we go from the mean, we have a plus sigma on one side and a minus sigma on the other side. So that's the definition of that sigma. You hear in the Gaussian distribution, you know, the sigma, it's not the full width at half max. Notice this isn't halfway down. I'll just go ahead and put that in just for grins. This down here is the full width at half max. So halfway down from the maximum full width of the curve. And so that, notice that is not equal to plus or minus sigma. Okay, it's just a little bit bigger. Now, if we took just a plus or minus 50% confidence, that would be these green marks. And so what we're saying is, this is the confidence interval around our mean that contains the true density. So we measure the density, but we don't know what the true density is. And so we can say if it fits this Gaussian curve, the true density is somewhere between these two green marks, or at least we have a 50% chance of the true density being between these two marks, because the area under this curve is 0.5 between these green marks. But look at how many metals that contains. That contains tungsten, tantalum, gold, rhenium, platinum, osmium, and iridium. So it's almost a coin flip with our measurement that it's one of these elements or not. Okay. Now, if we went to 95% confidence, we'd have this range. So notice how the more confident we are, the less certain we are. We're less certain because we're including so many metals. So we're 95% confident it's one of these metals. Okay. Yeah, I mean, that's something, right? Because it's not magnesium. I think magnesium's over here. So if magnesium was the thing we were worried about, even with this crummy measurement, we could be 95% certain it's not magnesium. So, you know, it's not the greatest experiment in the world, but it definitely is useful for some things. Okay, we have less than a 5% chance of it being magnesium with this measurement. Because think about it, we measured its density and it was 19 something. And magnesium's density is 3 point something. Okay, so it's so far away from 3 that we can be 95% sure it's not magnesium. So you might say, yeah, but the math worked out so that the number was closest to tungsten, but there's no yeah buts. Okay. When my kids were little, I wanted to have a hat that says, my name's not yeah but. You tell them, you know, did you make your bed? Yeah, but time to quit playing the game. Yeah, but I'm almost done. Or I'm in a boss level, you know. So every measurement has some uncertainty, even if you don't know what that uncertainty is. And so even though our calculator told us it was 19.25, we really don't know anything about those decimal places. We were uncertain in the ones place, right? We can't say that it's 19.25 at all, because it's 19 plus or minus 8. Yeah. And when I talk about these bridges falling or whatever, this was a few years ago. Engineering had messed up on the corrosion resistance of this bridge, and the girders had corroded, and people are driving to work during rush hour in Minnesota, and this bridge over the lake just goes bam and breaks, and cars drive right into the river, and it's dramatic. Also, it was a Mars vehicle. It took billions of dollars, obviously, to send this vehicle to Mars, and they had done the unit conversion twice. Okay, so they converted to, I guess, English to metric, and then converted it again because they didn't carry the units forward and tell the next person that they had converted it already. And so then they had the wrong trajectory. And so they came in and skipped it off of the atmosphere and lost communication. So it's tragic. And so we can't tell with more than 50% confidence that it's one of these, but we can be sure that it's not magnesium or one of those really light elements. Now that's the example that was in those PChem notes. Let's do one that's directly related to this course, and that is calibration, because if you're going to be doing instrumental analysis in a forensic laboratory, you're going to use calibration curves. And so here's an external standard calibration. So we've taken external standards of cocaine, and put them through our instrument at varying concentrations. And so you can see the parts per billion cocaine across the x-axis, starting with really low amounts, like maybe 20 parts per billion, going up to over 500. And this is the trend line that we get from this external calibration. And I have a problem with trend lines. I know you've probably used them in your graphs if you're doing undergraduate research or what have you. And they are useful to some extent, but the problem with them is that they don't show the uncertainty. So we get the M value and the B value, but we don't get the plus or minus. Okay, and so if we go in and then measure a Y value like 3 times, then it comes across and hits our calibration line and gives us our X values. And we don't know what those X values are in terms of their uncertainty. We could average that Y, come across and get an average X, but what are the error bars on X? So you see the question that we need to ask. How do we propagate this uncertainty? Because now it's no longer just multiplication or division or subtraction or addition, it's both. We have MX plus B, and so we have to take into account both of those. And then also this trend line is not useful because it doesn't give us the information to do this problem. We need the uncertainty in M and we need the uncertainty in B. So we need to do the full ANOVA. We need to put in the analysis of variance. So we need to do the linear regression, not just the trend line. And y'all know how to do that from Excel, from PChem1. You go in and you select your X values and your Y values, and you put those in the linear regression dialog box, and then you get the regression output, and it gives you the analysis of variance that tells you what M is and a standard error in M, and tells you what B is and the standard error in B. And so this is what we get in terms of, move this little zoom window down here. Okay, so this is what we get for the output. We have the standard error in B and we have the standard error in M. And so now we can go from that regression output and we can write the standard error here. And this goes right here. So we could write our trend line in a better way now with the results from our ANOVA output. And then this one goes here on the M value. Oops. So do you see where those numbers come from? Yes.
So I know that the R-squared value doesn't give you the uncertainty in the M and the B. But
Doesn't give you the what?
The uncertainty in the M and the B.
Yes.
But doesn't it tell you how closely the line fits the data?
Yes. So let me, I'll see if it'll keep my, yeah, okay, let's look at this. So if you look at the data, it changes. Okay, so the data changes. If we had these 5 standards and they came in at 50,000, let's do Y here. Y. And Y. So what's our model? Y equals 50,000. Okay, and notice there's no X in there. So there's, if we modeled this with a trend line, our R square would be 0 because there's no variability in the data at all. Okay, and so with our actual example, we have quite a bit of variability. If we plot Y versus X, our eyes, now that you're trained as a chemist, you see it's a linear trend. You see just straight line. Even if there was no trend line, you would be there. Believe me, you've come a long way. We asked that question of the freshmen when we do kinetics, and you say, okay, is it a linear with inverse concentration, or is it linear with the log of concentration? And they have no idea what we mean by is it linear. Okay, so I don't know if, but you were probably there at the freshman level. You're like, what do we mean by linear? Now you look at those data points, those blue points. If there was no line there, you're like, wow, that's a linear trend. I'm going to put a linear, trend line on that, and I'm going to get a high R squared. And so what this is, R squared is the if you do 99.94%, so you basically multiply by 100% of the scatter in the data is captured by the model. Captured or maybe predicted. So you have this model and it's predicting 99.94% of the change in Y with respect to X. So that's a great way to think about it, is that it's a percent of the data scattered that's captured by your model. And so it's telling us that there's a, 0.06% scatter of that data that's not captured by our model. Is that random stuff? I don't know. It could be a quadratic part. It could be a sine wave part. It doesn't have to be random, but it's just not captured by our model. So we don't know what it is. But the linear part of the data is captured by our model, and then we're capturing 99.94% of that scatter. So anything other than just a constant number is scatter in the data. So that's really good. And so then we still have uncertainty from that model because it's not a R squared of 1. It's not a perfect fit. And so that uncertainty has certain portions to it. It has a portion that's related to M and a portion that's related to B. And I'll show you the equations on how we get all of those different pieces. Okay, so let's look at those. Propagation of uncertainty in a linear fit. So we have this given Y value plus or minus SY. How do we find SX? So here's the information that we have. We have M is equal to 416.6 area counts per parts per billion. So that's the units. How do I know the units? Well, let's look back at what the slope would be. The y-axis is area counts, the x-axis is parts per billion cocaine, and the slope is rise over run. So rise is the y value, run is the x value. So the units on our M value are area counts over parts per billion. What's B? B is the y-intercept. It only has units of y. Okay, so just getting the units right. The units all work out, and if the units aren't working out, you've done something wrong. So it's just a great guide in any of your chemistry problems is to look at the units. The uncertainty in M is going to have the same units, area counts per parts per billion. Then B is just area counts, and here's the uncertainty in B. So all of this is from the ANOVA table. And then we run 3 check samples. So now we get into our unknown Y. So we run in some check samples, unknown parts per billion, cocaine, and we get these 3 peak areas from our chromatogram. We average those and take a standard deviation. And so now we have Y and SY. Okay, so now we know our Y numbers, then we're going to propagate over to our X numbers, calculate our parts per billion. And so Y is 55,333 area counts, and then our uncertainty in Y comes from our standard deviation of the 3 runs. If we just ran 1, we would get a Y value, and we would have to assume that the uncertainty is 0, which is a bad one. I mean, that's a bad assumption, but that's all you've got sometimes. So if you just ran 1 on this model, you wouldn't have any uncertainty in Y. So what is X? So we have our Y value and we need to solve for X. So we have all of, we have Y, we have M, we have B, and so we need to know what X is. So that's pretty simple. We subtract B from both sides and divide by M. So just a little bit of algebra, no problem there. So X is 55,333 minus 1214 over 416.6. And so X is 129.9 parts per billion. I'm going to keep all those digits for now, just to see where to round later. And that's pretty easy. You did that at freshman level. You calibrated your spec 20s, you put in an unknown, you calculate X, you're good. You got your concentration. But what about the uncertainty? That's why we, it takes so long to get to that. And so we don't know what our uncertainty is in X, and we need to propagate the uncertainty from all of these other values. So we have lots of SB, SM, SY. We have lots of uncertainty values to incorporate. So this is our calculation. Notice that we have a subtraction piece, and that has one way of propagating uncertainty, and we have a division piece. So this is a two-part problem. There's no way to get around that. And so that's, so we have a numerator. Let's just do the uncertainty for the numerator. So numerator is y minus b. So that's that 55,333 minus 1214. And so this, this doesn't have a variable associated with it. I'm just going to call it numerator. Okay, and then what's the uncertainty for the numerator? Well, that's the sum of the variances of y and b. So the variance of y plus the variance of b, take the square root and we get the uncertainty for the numerator. Are y'all cool with this? Would you have been able to find this equation? Right? If they break this into two parts, you do the addition and subtraction first, just like you would on your calculator, right? If you're calculating this, you're going to take b and subtract from y before you hit divide. Okay. Now, some people may say y divided by m minus b divided by m, but it just makes the problem longer. The order of operations, you're going to do the subtraction first. And so the same order of operations will guide your uncertainty calculations. So let's do that subtraction first, and let's find the uncertainty in that number first. And so we get the uncertainty in the numerator as 1532 counts. And so now we have the numerator divided by m. We have the uncertainty in the numerator and the uncertainty in m. So those are going to be the relative standard deviations. Would you be able to do that now? So we have this numerator on top and m on bottom. So that's a division. And so then we're going to have this value times the square root of the two RSDs, the RSD of the numerator. Notice this is not the RSD of b. This is the RSD of the numerator. So that 54,119 goes in the bottom here, and this uncertainty for the numerator goes on top. And then we have SM over M. And we also have our X value, 129.9 parts per billion. So if we calculate this, we end up with an uncertainty of 4.1 parts per billion. So we keep our two digits, so we can report that number of 129.9 plus or minus 4.1 if we were just doing plus or minus 1 sigma. So I'm going to sit here and pause and give you a chance to ask questions. Yes.
What if the standard error doesn't have a decimal place?
Good question. Look at the like B up here. So up here for B, we've kept two decimal places, or two significant figures, not two decimal places. We've kept two significant figures of our uncertainty. So how would we report this, right? I went ahead and kept that 4, but honestly, I shouldn't, because I'm uncertain in the hundreds, very uncertain in the tens. I have no clue about the ones. Okay, so you probably could report this. If I just asked you to report B, you would report this. Okay, and trailing zeros are not significant without a decimal place. And so I'm telling you that my uncertainty is in the tens place value. But if you're worried about me not following your ironclad logic there, then you can always write it in scientific notation. And so you could write this as 1.21 plus or minus, let's see, 0.12, right? Times 10 to the 3. So notice I've moved the decimal place 3 places on each of these and reported it to 3 significant figures, because that's what I have. And so my place value matches. It's in the hundredths of this number, times 10 to the 3. Another way to write that would be 1.2 plus or minus 0.1 times 10 to the 3. Or this is what you'll see a lot of times in the literature with the parenthesis 1 there, times 10 to the 3. So that's showing as 1200 plus or minus 100. And that parenthesis tells you the previous place value is where the uncertainty is located. Okay. If you wanted to keep two decimals or two significant figures of uncertainty, you could do 1.21 parenthesis 12 times 10 to the positive 3. Okay. So these are a bunch of different ways to report that number. Whichever one you think is the most unambiguous, you can use. Because it's about communicating. Yes.
So you mentioned that the plus or minus can also be written as parentheses.
Yes.
And on the homework, like just one of the numbers, it's like 0.500 parentheses 4.
So let me write this out. 0.500 parentheses 4.
Yeah.
Okay.
What would that be? Would that be like 0.500 plus or minus?
Yeah. So let's go ahead. We've got this number. Let's write out what. Let's say this is A, right? So A is equal to 0.500, and SA is equal to 0.004.
Okay.
Yeah, you see, so what you're saying is that previous digit or previous place value is where the uncertainty is, and the magnitude of my uncertainty is 4.
Mhm. So if there's only one number there, it's going to go at the last place.
Yeah. Yes. And so on this one right here, let's look at this one. We have this number here. We'll say A is equal to, I'll keep it in scientific notation just for grins. So A is 1.21 times 10 to the 3rd, and SA is equal to 0.12 times 10 to the 3rd. You see it? So even in scientific notation, that parenthesis tells you the place values to replace, and the number tells you the magnitude to put there. And so since I have 2 numbers in the parentheses, it replaces the previous 2 place values. So here I've got, see these 2, since I've got 2 here, I'm replacing both of these numbers, and everything before that's a 0. Just like this 4, I'm replacing that place value, and everything in front of that is 0. I'm just trying to find out where my uncertainty is and what the magnitude is. So the 4 goes in the 3rd place value, and everything in front of it is a 0. So that's my uncertainty. And so that's, and if you were to go, and I may show you this later, I don't want to run out of time, but if you go to the NIST website that produces, like reports all of the physical constants for nature, I mean the gravitational constant and Avogadro's number out to 6 decimal places and so on. That's how they write it. So they'll write out the number with the parenthesis, and sometimes the number in parentheses is 2 digits, sometimes it's 1. It just depends on how who reported those numbers. And so you need to know how to take that parenthesis number and come up with that uncertainty value. Excellent. So now we have our number, so we could report this as 129.9 plus or minus 4.1 parts per billion. So a lot of times when you're reporting numbers, you need to say that this is like in the literature, like when you're writing about this and you say the reported value is given, such and such as 129.9 plus or minus 4.1, where the uncertainty is plus or minus 1 sigma. So that's what we're reporting right now, but we could report a 95% confidence interval. So that's a different interval. That's sigma times 1.96. And so you need to tell somebody whether that plus or minus number is sigma or 1.96 times sigma or some other kind of multiplier times sigma. So it's definitely important to communicate what is the plus or minus represent. Many times it's just sigma, but you need to tell people that that's what you're using. And so plus or minus 1 sigma, just for your reference sake, I'll write it over here. Plus or minus sigma is 64% confidence. Remember, it was a little wider than our 50% confidence in that earlier chart. The area under the curve with plus or minus 1 sigma is 63.5. So it's 64% confidence. So everything inside that area covers up, you have a 64% chance of something in between 1 and plus or minus 1 sigma being correct, being the true value. So this is a busy slide, but everything's all on one page. So hopefully that helps. Okay, so let's take our Kahoot. Let's go back to the Okay, and if you're on Zoom, you can just bring up a browser and go to kahoot.it. You don't have to use your phone. If you're already on the computer, go ahead and just play it in the browser. Let's see. Okay, live game right here. See who gets on the leaderboard today. Where's my music? It's gonna be loud. Yeah, watch out.
You want our semi-use?
Yes, please. If you use your username, yeah, and then keep track of who played. I've got too many windows open. What's wrong? It's probably really loud on their computers. I don't hear it on ours. Strange. Let's see, we've got 19, 21 in the class. Okay, you're not in yet? I'm gonna go ahead and start at 3, 2, 1. Yeah. I didn't realize that. You can join a game in progress. Okay, cool.
As long as they use that same code.
Yeah, gotcha. And the code's on the screen. What's the why use the standard deviation instead of the population sigma for a small data set? It's just not the same without the music. Yeah, we can sing along. Pick your favorite answer if you think. Oh my gosh, no. So it's accuracy is not really used to it's hard to know what the true value of an uncertainty is. And so we don't really use the term accuracy for sigma. So it's just put that in as a distractor. But yeah, the S is larger than sigma, so it's a more conservative estimate. So both of those are kind of the same answer. So, but this is like only 4. Okay, so that's why we reteach, right? So we're looking for being the most careful, right? If I'm reporting my uncertainty, I want to make sure that you know what my worst possible situation is. And so we report the bigger uncertainty. Which estimate of uncertainty is the largest relative to the mean? We have several different things reported here. Just a little boop, boop, boops, but I don't hear the music. There we go. Good job. Okay, this may be it right here. Anything? No. All right. So yeah, the 6 inches. I have no idea what that is about. Okay. CV is coefficient of variation, and it's RSD times 100%. So that would be 0.35 RSD. This 560 parts per million could be a coefficient of variation for some process that's got almost no uncertainty at all. So that would be 560 times 10 to the minus 6. So that's the parts per billion thing. And so then this is 0.75, or if you were to convert that to a coefficient of variation, that would be 75%. So that's the highest uncertainty relative to the mean. Okay. Just 2 more. The needle is exactly between 2 tick marks labeled 7 and 8. So what do you write down? I got some more sound stuff. This is kind of a review from the last set of notes. Yay, look at that. Fantastic. So you're instructed to try to estimate between the tick marks if you can. And if you see that it's right between the 2, you can write down 7.5. And so you're certain that it's 7, and you're uncertain in the 10th place. And so that's legitimate. All right. Last one. When you're reporting the precision of multiple groups, what do you use? Try to remember. This is a vocabulary. Very good. So it's that pooled standard deviation. The population means like the population of all possible measurements in a particular, like one person measuring I guess it goes back to, I don't know if it goes back to social science or not, where you're actually trying to get the preferences of a population, right? But if you're looking at doing titrations, right, that acid concentration, you treat it like you shake it up and you do several measurements. There's a population of measurements, right? Or a sample of measurements. And when you have 15 or more measurements, you have a population, and you're sort of characterizing that bulk solution. So it's still a single analyst, a single technique, and that's measuring that particular population. All right, let's see who we get. We'll do metals. This is kind of, I don't know what this is, pentagons. Okay. Always fun. So let's look at just this idea of this Gaussian. We were using Gaussian statistics, but what's the basis of this Gaussian curve? If we're thinking about a single true value, so we have the true value of a given measurement. As that true value is percolated through your instrumentation and this natural fluctuations and so on, it can be distorted. It can be distorted high or low. Notice the true value is not changing, but this distortions make your measurements miss the mark. Think of looking through water at the lines in the swimming pool, right? So the top of the water is moving around and those lines are moving left and right. If you were to take snapshots and mark where that mark was on a ruler on the side of the swimming pool, eventually if you made a bunch of marks, you would have like a Gaussian distribution of where that line is. And so that's kind of what's going on. You have your true value, and the distortion that the water is doing for the swimming pool line is doing the same thing to your true value. So you have a concentration of cocaine in this example, and you measured it a bunch of times, and you keep getting different numbers because, like the water in a pool, that true value is being sloshing in your result around. Once you have enough fluctuations, they lead to this Gaussian distribution. And these are random fluctuations that would lead to the Gaussian distribution. If there's a bias or some sort of trend, then you don't have a Gaussian distribution. You have a skewed distribution. And so what we're looking for is we're trying to give our mean and standard deviation times some factor to give confidence that that true value is somewhere between those limits. And so if nothing gives us a systematic shift, high or low, then that mean is here, and the let's say 1.96 sigma would be our 95% confidence interval that would get us out here. And we could say we're 95% confident that when if we were to extrapolate these confidence intervals up here, that our true value would be between those limits. So we're trying to go back to that true value, and that's what our confidence interval is about. And we're saying that there's a 2.5% chance that it's high and a 2.5% chance that it's low. So it might be out here. X2, X2, let's do X2, X2. So there's a 2.5% chance that we just got so many high measurements that our average and standard deviation ended up high, and our true value is really below that lower confidence interval. And so we're comfortable with that. Sometimes we go to 99% confidence so that there's a 0.5% on either end. And so what we're looking at is that those areas under that curve, I said 64%, maybe it's 68. Yeah, so I was a little bit off on that. This is the confidence interval of plus or minus 1 sigma. So it's 68% confidence. If we go to 2 sigma, it's 95.4. So you notice that little 4 on there. And so if we don't like the 95.4% confidence, if we just like 95% confidence, then we actually put our limits right here at 1.96. So if we go to plus or minus 1.96 sigma, then this 0.4 goes away and we have 95% confidence. Okay. And then if we went to 3 sigma, we would cover 99.7%. So rarely do we use sort of integer multiples of sigma. We typically use what's called a z-score of like 1.96 for 95% confidence. Okay. And so that's what we're talking about with these confidence intervals. It's a range of values derived from the sample statistics on our measurements that's likely to contain the true value of an unknown quantity. And so if we did this experiment 20 times, there'd be 1 chance out of that 20 that we would miss the true value with these. So that's pretty good. 19 out of 20 times, your true value is going to be between your confidence interval limits. So yeah, I say that's good, 19 out of 20, but if you're dealing with taking away someone's liberty, like in the forensic system, that's not very good, is it? And so that's why we use multiple techniques. And so this might be the confidence interval for the GC, and then we also have an IR, and we also have a spot test, and we also have other evidence. So you have all of these techniques, and all of them have holes in different places. So you might get past one out of 20 times, but it's let's say it'd be 2.5% on one side of that and 2.5% on that. So 0.025 times 0.025 would be your probability of getting past both of them. And that would be a much smaller percentage. And so that, again, this range of values is derived from that distribution function, the Gaussian. So these are using Gaussian statistics. And so here's the practical consideration. Even 99% confidence stinks if you just have one measurement, because that's 20,000 lost articles of mail per hour. Or unsafe drinking water 15 minutes per day. Which 15 minutes? I don't know. 5,000 incorrect operations per week. 2 long or short landings at most airports each day. 200,000 incorrectly filled prescriptions every year. So again, we want to operate it even better than 99% confident. And that's what we do. We take multiple instrumentation or multiple analysis methods and couple them together. But this one here with just in like 2008 number, 16,000 murders, that's 162 wrongful convictions. So if we were just using one method at 99% confidence, this is the thing that would result in it. So that's why we use multiple methods. And then we also are safe if there's conflicting data, then we say there's, you know, inconclusive. One analysis method says, you know, I use the term controlled substance, and the other says, no, it's not, it's inconclusive then. So it has to be clear and convincing evidence. So this is surprising. You know, we deal with 95% confidence all the time, and here's 99% confidence, and it would yield these kinds of results. So what do we want? We would like to have 6 sigmas instead of just 2 sigmas or 3 sigmas. 6 Sigma is a quality organization that attempts to design quality into a process, and it seeks to have less than 4.3 defects per million. And it's per million opportunities. So in an automobile, if you think about all of the parts on an automobile, there's definitely more than a million opportunities for a defect. And a defect could be anything from a cross-threaded screw, a blemish on the paint, you know, a serious one like you know, maybe a combustion cylinder that's out of round or something like that. You know, some defects are going to cause mechanical problems, others are just cosmetic, but they're still defects. And so there's not an automobile that's produced that doesn't have some defects, but they would like to keep it below 4.3 defects per million opportunities. And so that's their goal. And that's, you need to be 6 sigma away from your nearest specification limit on all of those little processes. And so that's, you know, that's quite a goal. But it would be nice if the forensic science community could move more towards 6 sigma in all of their processes. And one of those things that helps with 6 sigma quality control is control charting. So that's why I make such a big deal of that in this course, is because I want for you to realize it's not that hard to do control charting. It requires discipline, but if you pick something that's done in your normal routine, then it's not an added burden, and yet you can follow the process very well. And you can see when there's a problem before it becomes a problem for your customer. You can see when there's a problem internally. So let's, you know, that's why we're focusing on control charting. So there's some other examples for the propagation of uncertainty. And again, these are some examples, kind of like this one using the parentheses method here. So this 1 ml stock solution containing 1 milligram per mil. And so here I've written it out with the parentheses. And so down here, this is turned into this, right? So this example is kind of showing you how to use that. And so then the RSD is 0.01 over 1, and then the CV. We have this stock solution that's prepared, but we don't know the uncertainty in it because that's sort of our Y value. And then we have 250 microliters, and in here we've written the uncertainty in percent. Okay, so that's a CV value. So how do we get from CV to uncertainty so we can do the propagation of uncertainty? So remember that the CV is 100 times the RSD. And so that's telling us that it's 0.5% over 100%. So this is our RSD, is 0.005. And so then that's the RSD, that's equal to the sigma over the Y value. So this is, in this case, we'll say B, right? This is B, and this is related to sigma B. It's not sigma B, but it's related to it. And so we're taking the CV, we're getting out of the 100%, and we're going to the RSD, and then the RSD is equal to this. And so then we can get to that sigma B. So 0.05 times 250, this is our uncertainty, 1.25 microliters. So you need to be able to go forwards and backwards in terms of your uncertainty, especially if they report uncertainties in terms of percentages. Okay, and here's another one that's reported in a percentage. So CV is 0.03%. That means our RSD is a really tiny number. And so then this times 250 gives us the uncertainty. So here's our sigma C. So these are some good examples, and I would say just, work through them and, be able to work these problems. Yes.
So the uncertainty, the 2 plus or minus 0.5% is reported as a coefficient variance, but what could it ever be reported as the relative standard deviation? And so how would you tell the difference between the RSD and just the regular sigma?
Well, that's a good point. I clued in that would, like, if I was looking at this problem fresh, I would see that percent and say, oh wow, that's a coefficient of variation. But if I just saw like 0.005, then that would be a really misleading thing. So if we put this number in here, then I wouldn't know what to do with it, because that would look like 250 microliters. And then plus or minus, well, the plus or minus, yeah, you wouldn't use the plus or minus the RSD, because it's a relative standard deviation. So this wouldn't be there. It would be 0.005. And again, they would have to leave the units off because the RSD is unitless.
The place value kind of give you a hint.
It would make me wonder. I was like, man, that is some
So small.
serious volumetric flaskage, and a 250 microliter. Or no, let's see, that's the syringe. That's a heck of a syringe to have, uncertainty in the thousandths of a microliter. Yeah, so that would be really, I would wonder what's going on there. Now they might say, if I just wanted to use that, let's say that was on the box, and I was just saying, okay, this is the reported, I would say 0.005 RSD. And so there I'm labeling it RSD. I'm not multiplying by the RSD, so I would say this is the RSD number. So, but you're right to clue in, like, what if that was just a decimal number? What would I do with it? And the answer is, I don't know. This was the thing that would clue me into it being a coefficient of variation.
And then we calculated the sigma using the RSD, and this equation for RSD is sigma over the mean, but you can just put the number in.
So yeah, so here I have RSD, all of these are equal to RSD. So this number is equal to these.
Yeah.
Yeah. And so then I just multiplied the 0.005 by 250. Yeah.
So you don't have to have a mean, you can just put the number in there.
Yeah. So it's sort of, I guess this would be, even though we say it's the sigma over the mean, we're assuming that this would be the mean value, even if it's just one number. Yeah. Great questions. And so you can go through these and look, and then the next thing is, again, this is a dilution problem. So it's M1 V1 times M2 V2 or equals M2 V2. And so you can see all of the algebra here for the propagation of these. So go through these. These are all worked out for you. Just make sure you understand them all. We don't really do much with the logs and anti-logs, but I just included them. They were in the PChem set of notes too, but I went ahead and pulled them forward just so that you have access to them. All right.